Okay. So lattices, and symmetries. So let's first consider the Hamiltonian, right? In physics, we are solving the Hamiltonians, and typically Hamiltonian decides what's going to happen. Hamiltonian. Hopefully you can read, right? It's not too small. Okay. Let me know if you can't. Hamiltonian. Something like that. H is equal to somewhere all I, pi squared over 2m plus. Typically we write it like this to prevent double counting. This is I bigger than j. And there's some interaction potential, Ri, so this is a vector minus Rj. So this could be just electronic system and electrons, but it could be also more general, like electrons, protons, everything is labeled by these coordinates. So Ri and Pi are position and momentum of all particles, whether they're identical or not. If you want, you can also put like an index to mass, but since I'm not going to use it, I'm not going to do that. All position and momentum of all particles. Good. So what are the symmetries of this thing? So the symmetries, there is first translational symmetry, right? If you look at the Hamiltonian translation, so each Ri, you can take it to some Ri plus delta for all I, for all particles, you can do that. And you can also do that for like small or big delta, right? Because if you put a shift, right, momentum is the derivative. And if you put like a constant to the variable, the derivative will not change. In the second one, there is like the difference between Ri and Rj, because you are shifting everything with the same amount. So the second one will not also change. So this is like translational invariant. Similarly, it is rotational invariant. Rotational invariance. So any R, take them, like if it is like three-dimensional vector, you rotate three-dimension. If you are in two-dimension, rotate two-dimension. And there is like some rotation matrix. And so this is Ri. So this is a little bit harder to show, but since R's are like orthogonal matrices, right, the determinant is going to be 1, and also the invariance can be shown. Another one is space inversion. Space inversion. This is sometimes called parity, and P for parity. And for this, you need to like specify a point. This is with respect to a point. Let me call it R0. And the inversion works like this. You have like some Ri with respect to this point R0. This is going to minus of itself, right? This is Ri minus R0. So this is the inversion. So there are more symmetries, but we are going to start with these. And typically, for example, like it depends on what kind of like material or substance you have to speak about these symmetries. For example, if you have liquid or gas, they have, okay, this one is Tr, this one is R. They have translation symmetry, they have rotation symmetry, and they have parity. And to say that the liquid has these symmetries, you can consider any kind of observable. For example, Gervin and Young says rho of R, for example, the liquid density. Any observable fine, but they are all going to be translationally, or they are all going to be symmetry invariant like this. However, solid is not, right? Solid, if you want like something like this, you have like atoms separated. Okay, I'm drawing like a one-dimensional cartoon, but you can generalize it to 2 and 3 dimensions. And we say that in a solid, symmetry is spontaneously broken. So why it's broken, we don't care. We can also speak about that. There's like interparticle interactions, and they can minimize their total energy when they are arranged in a particular solid or crystal form. But for this course, we don't care. There's like some mechanism that breaks the symmetry spontaneously, and that's our starting point. And that's why we have a crystal rather than liquid or gas. Okay? Therefore, the problem in condensed matter is to find ways, like mathematical methods, to work in a crystal environment. Okay. Thus, we need to work with crystal structures. And today, and maybe in a couple of lectures coming ahead, I'm going to spend some time to formulate a formalism to study crystals. And the first thing we need to speak about in a crystal is so-called Bravais lattice. So this is a set of points that you can enumerate like this. There's like some R that depends on tuple of 3 or 2 integers depending on the dimension, and so this n is n1, n2, n3, right? These are integers, and I can like span all crystal points with a set of basis vectors, like something like this: n1, a1 plus n2, a2 plus n3, a3. These are vectors, but sometimes I may forget. And these are primitive lattice vectors. We can, like, I think, consider some examples. Actually, let's go to Mathematica. I think it has. So, for example, let's start with. So, in Mathematica, there is like there are many comments, but you can Google it if you want. Something like this: lattice data. And let's start with simple. Okay, if you just, I think something. If you do something like this, it gives you all possible. Here. Okay. So all possible definitions are here, and you can just, for example, take, I don't know, let's start with simple cubic, and let's see the image. Okay, this is simple cubic, right? Like, you have to repeat this in all directions infinitely many times to get the full crystal structure, but the unit cell is something like this. Okay, something like that. Now you can also look at the basis vectors. Let me copy that. Here's the basis. You need to normalize it. So this is like sparse matrix. We can do the normal, right? This is like a unit vector in x direction, y direction, and z direction. Simple stuff. Similarly, you can do, I don't know, let's do it. There are like 3 basic 3-dimensional structures. It's the simple cubic, body-centered cubic. So here has the basis vectors, and you can also look at the image. The body center is like a cube, but additionally there's like one more atom at the center, and these are the basis vectors. And lastly, there's one more. There are many more, but these three are good enough for us to get the hang of it. There's also face-centered cubic, and in the face-centered cubic you put like atom in every face, right? There's like a cube, and you have atoms at the corners, but also you have like atoms at the centers. And you okay, this is easy to it's easy to write the basis vectors like this, but let's also get it from Mathematica in case you forget and you try to get it real quick. It's there. Okay. So let me just write one, and the others you can get from the Mathematica or internet if you want. So a simple cubic. A1 is AX, A2 is AY, and A3 is AZ. And this A without an index is what we call lattice constant. Good. So every side in a Bravo lattice has the same number of nearest neighbors, and that's called the coordination number. So the coordination number is number of near neighbors. For example, in a simple cubic, so coordination number we show it as Z, and you can draw your cube and look at the nearest neighbors. There's like 6 in simple cubic. So let me, Z is equal to 6 in simple cubic. 12 in FCC, face-centered cubic, and 8 in BCC, body-centered cubic. So, okay, this is coordination number. Another concept is so-called primitive unit cell. Primitive unit cell. It is the cell when you translate it to all lattice points that spans the entire space, right? Typically, like the choice is not unique, but we don't care. Like a good choice is like the parallel piped by vectors A1, A2, and A3, right? There's like a cube you can form from these, or cube, or like some parallel pipe, you can form these 3 vectors, and that's the primitive unit cell. This is another concept. There is so-called Wigner-Seitz cell. Let's Wigner-Seitz cell. This is the primitive unit cell closest to a given site. Like this is primitive. So this one doesn't have to be on the site, but this one centers on the site. This is primitive unit cell around a site. Let me illustrate. For example, let's consider it's easier to draw 2D, and many interesting examples in this class are going to be 2D. So very rarely we'll have to do 3D crystals because most concepts are in 2D, and it's easier to draw anyways. So let's consider 2D square. It is something like this. Right. And for Wigner-Seitz, let me use red. So I choose like a site. Let me choose this central site, and I look at the nearest neighbor here. This is the nearest neighbor. I draw a line. I look at the nearest neighbor here. I draw a line. I look at the nearest neighbor here. I draw a line. And here is the nearest neighbor. I draw a line. Here's this one is Wigner-Seitz cell. Let's also draw the usual primitive cell defined by these parallel pipes. This is like this one, right? You just span. You just choose. This is primitive unit cell. And here we can also define something called point symmetry. Point symmetry is all transformations that keeps a given point unchanged. For example, if we are talking about this point, there is like a rotation by like pi over 2, right? There is like a reflection by this point. There is a reflection like this. You can reflect it like this. All of the, or you can rotate by pi. You can rotate by 3 pi over 2. These are all symmetries of this point, and we call those point symmetry. So let me give another. This Wigner-Seitz cell being translation, like simple shift of primitive unit cell, is not always true. Sometimes it is not. Let me give you another example. 2D triangular lattice. Let me try to draw it. I need a little bit more space. So it's something like this. I have to put triangles, right? There's another triangle, another triangle. Okay, let's draw Wigner-Seitz cell with blue, color blue. Here's, let me choose this one. The nearest neighbor is this, and perpendicular is like that. Nearest neighbor is this, and perpendicular like that. There's another nearest neighbor here, another one here, another one here, another one here. Since my drawing was not perfect, it was a little bit crooked, but that's fine. You can see it's like a hexagon, right, with the vertices here. So this is, okay, here I use blue for primitive unit cell. This is for Wigner-Seitz. Sorry about that. This is Wigner-Seitz. And the unit cell, you can see, here's the unit cell. So this is primitive unit cell. So they are not related as simple as 2D square. Good. Any questions? So let's talk about lattices with bases. Lattices and bases. So every crystal has a lattice, like crystal is equal to a lattice plus a basis, right? You give me a lattice, that's not enough. You also, like, there's like a rule to tile entire space, but you also need to tell me what I should put at these individual lattice points. In the simple case, one atom at each lattice point. For example, in this case of square, okay, here's the square, and I just put like atoms like this, right? So the lattice is the square, and these like circles I'm drawing are the bases. But in some cases, there may be more than one atom in the basis, right? So more than, sometimes there can be many, like there can be entire molecule in the basis, right? You are going to shift that molecule, and the periodic arrangement of this infinitely many molecules is going to be the crystal lattice itself. So many, more than one atom at basis is possible, and the people sometimes call this non-Bravais lattice, right? Bravais lattice is the one like this. non-Bravais is the one that you need more than one atom per the basis. And I think the example we care, and that will be, I think, very illustrative, is going to be graphene. Maybe I can try to find a drawing rather than. Okay, this is a little bit like a bulky picture, but that's fine. In the case of graphene, we have two inequivalent sites. We have so-called A sites, and like all atoms here are carbon, but because of the crystal structure, two sites are inequivalent. And let me explain. So, for example, this site, okay, blue, all of its neighbors are going to be red. So this one, and this one, and all of the neighbors of okay, this picture is a little bit disorienting, like this one and this one. For example, I jump on this and this, and so on. Red, color red, this one red, this one red, and this one red. And if you look at like the blue sites, all the blue sites, for example here, I have like a, let me use another color. So this one is the basis vector from blue to blue. Here's a basis vector from blue to blue. And there's another basis vector from blue to blue. Another basis vector from blue to blue. And you can see this diamond is exactly the unit cell of triangular lattice, right? We have two triangular lattice on top of each other. And there's like a blue triangular lattice and red triangular lattice. And red triangular lattice is shifted to the center of the blue triangular lattice, right? That's the graphene. That's the lattice structure. So let me call it underlying Bravais lattice is triangular, but two of them overlap with shift over. And this is not specific to 2D. For example, in 3D, diamond also has this structure. Silicon also has this structure. I think gallium arsenide also has this structure, but each basis state is occupied with gallium or arsenide in the case of gallium arsenide. How many people know this? Right? Everybody knows this, right? Okay, good to. It'll be boring for a couple of lectures, but we'll be on a firm ground. It doesn't hurt. I think in Mathematica you have. Let me give you an example. I think it is like. I think Mathematica will complete for me. Let's see. I think it is. I took a note here. Tetrahedral packing. They don't call it diamond structure because they are mathematicians. So this is tetrahedral packing and image. Here's if you want, this is like a 3D graphene, right? So there are like two FCCs. There's like corners, and also the faces of the cube are filled with one basis atom. And if you shift all of these guys, maybe this one is easier to see. So this corner is shifted like this. This face atom is shifted like that. Another face atom is shifted like that. And these two atoms, these two overlapping three-dimensional lattices fill the entire space. And if, so this is A type, this is the B type. Maybe I can look from a different angle. So this one is A type, this one is B type. In the silicon and like diamond, A type and B type are all the same. In the silicon, in the diamond it is carbon. In gallium arsenide, one is gallium, the other one is arsenide, for example. Good. So the coordination number in graphene, coordination number Z. What is Z for graphene? Look at this atom and how many nearest neighbors does it have? 3. Z is 3. And there is a reason for this kind of crystal structure, right? Are these like substances are crazy? Why are they doing these like awkward arrangements? Maybe I can talk about that just a little bit. Carbon has how many electrons? How many? 6. Has 6 electrons. And it is like 1s2, 2s2, 2p2. And these are you can see the same shell electrons. There are like 4 electrons, and what they want to do is they want to hybridize, and they hybridize to sp3. And sp3 is, if you want, there needs to be 4 bonds dangling out from a site. And in the case of diamonds, right, like it is something like that. So this is carbon, and all of these, I think this is like 106 or something like that, I don't remember, but they are like tetrahedra, and every neighbor is another carbon. And if you do this and tile the entire space, you are going to have this diamond structure. If you do another thing, like if you do it in 2D, like this is like in 2D, so this is 120, this is 120, this is 120. So this is carbon, right? So there are like 3 electrons used for bonding. And there is 1 extra. What do we do with that extra electron? It's just free. That's what we study, right? That's like 1 electron is fully delocalized. And we are going to set up like a lot of formalism to understand the behavior of the single electron on the lattice, because it is like fully delocalized. It can go to any lattice. It doesn't belong to any particular carbon atom. It belongs to the entire lattice, and it gives very interesting physics, like for example relativistic quantum mechanics in like a 2-dimensional space. And this one, okay, gives, let me call it, semi-metallic behavior. Good. Any questions? So let me mention a couple of more symmetries, and I'll finish it today. And next time I'm going to talk about reciprocal lattice on Monday. Today only like real space lattice. Some lattice symmetries, not all of them, lattice symmetries. So we said the symmetry is spontaneously broken, but the crystal still has some symmetry. So before the broken translation, broken symmetry, we have a group, G. It has all possible symmetries, right? Translation, rotation, time reversal, parity, whatever symmetry you can think, it's there. But in the crystal state, you reduce the symmetry to a subgroup H. And this is what we call spontaneous symmetry breaking. Symmetry spontaneously breaks from like a larger group to a smaller group. If you don't know group theory, that's fine. We are not going to use it. It's just the terminology. Spontaneously symmetry breaking. But H, this little group, still has some symmetries. And they are typically discrete. And we call it like lattice symmetries. For example, we can have rotation by 2 pi over n, right? And we call this n-fold symmetry, n-fold rotation. Just a quick example is like square, right? I have this, and here n is equal to 4, and because of square, I have like 4-fold rotation symmetry. In the case of graphene, I have this, I have 3-fold rotation symmetry, and so on. Another symmetry is reflection symmetry. When we say reflection, we say that we have like some lattice, and there's like a nearest neighbor. We reflect with respect to the center of the bond next to the nearest neighbor, right? Like, for example, here, you reflect like this. So reflection. So there is inversion. So like this inversion is typically in 3D. In 2D, inversion is equivalent to like pi over 2 rotation, but we don't care. It's okay to like call them both inversion, because as long as you know what you mean, it doesn't matter. So 2D, it is pi over 2 rotation. And typically crystals with inversion symmetry, we call it, just to set up the terminology, centrosymmetric. It's a little bit old language, but every once in a while you see this in textbook. So this is centro.
Pi rotation or pi rotation?
Pi rotation, yes. Pi rotation. So this is centrosymmetric. When we say centrosymmetric, there's like an inversion center that you can invert or do this pi rotation. And then there's no, you can call it like, sometimes people call it non-centrosymmetric. So if you see that, that's what they mean. And depending on, okay, there are like many more symmetries, right? This is not like this. For example, in 3D, there's like 113 different crystal symmetries. You can classify crystal. We are not going to do that. If you are interested, you can look at the textbook. You can look at, okay, by the way, textbook. I will try to follow as closely as possible Gerwin and Young. Gerwin and Young. But I'm not going to cover everything. For example, this is like a chapter, this is chapter 3, and I picked the stuff I'm going to need for later material. So I will continue with chapter 3 a little bit on Monday, and then I'll jump a couple of chapters to like conduction, and then I will give you a little bit of like I will talk about Bloch theorem, all these things we need, and then we are going to talk about a little bit transport, and I'll jump to chapter 10, and then I'll try to follow chapter by chapter. Okay, any questions or comments? Okay, that's it today. I'll see you on Monday.